Good afternoon, colleagues. Today we will dive into the most intuitively accessible domain of machine learning, supervised learning. We will not merely unpack the technology, we will evaluate it from the practical perspective of our course, how high-quality data become the foundation of success, and how to manage the four key risks: bias, overfitting, model obsolescence, and the black box problem. And, of course, as per tradition, there will be a bonus quiz at the end to test your newly acquired knowledge. So be sure to subscribe, if you haven't already, to our channel, so you don't miss any upcoming lessons. Now, let's begin. Supervised learning is a machine learning method in which the model learns from examples where, for each input instance, the correct output or label is provided. Let's briefly revisit the fundamentals we discussed in the data lesson. Remember how we spoke about features, the measurable characteristics of an object, such as the square footage of an apartment or the words in an email. And we talked about labels, the very correct answers we want our model to learn to predict. These might be the price of an apartment or the verdict, spam. Labeled data, then, are nothing more than a pairing of features with their correct labels. It is this often costly and laborious process of annotation that transforms a chaotic collection of raw information into valuable training material. And I want to emphasize a key point: without reliable, verified labels, supervised learning is impossible, or, worse still, it can create the dangerous illusion of accuracy that may prove extremely costly for the business. Hence, supervised learning is often called learning from labeled data. You present the model with examples and their correct answers, and it learns to map between them so that it can correctly predict answers for new, unseen data. To grasp the essence of supervised learning, imagine two analysts. The first manually inspects emails, marking relevant features, sensational subject lines, the presence of hyperlinks, entries in the address book. He then assigns labels, categorizing each message as spam or not spam. His colleague maintains a real estate transaction spreadsheet, recording every characteristic of each apartment and precisely noting the sale price of each unit. In both cases, they create an ideal set of training examples for the machine. By gathering thousands of such feature plus label pairs, we effectively hand the model a textbook with the answers. What happens next? More formally, the goal of this learning method is to find the mathematical function that best associates our features, the inputs, with the known labels, the outputs. To evaluate this, we need to remember the concept of prediction error. Prediction error is a quantitative measure of how far the model's output deviates from the correct answer. Simply put, it's the difference between what the model thought and what is actually true. Having a ground truth allows us to do something critically important: measure that error. We can compute exactly how much the model's predictions diverge from reality. And our entire training objective becomes minimizing this divergence to a level acceptable for the business task at hand. Within supervised learning, there are two fundamentally different tasks. The first is classification, where we predict a category, spam or not spam. Approve a loan or deny it. The second is regression, where we predict a specific numerical value: how much will this apartment cost? The principal difference between them lies in how we measure success. For regression, we look at the average error: by how many dollars, or degrees, we missed the true value. In classification, however, raw accuracy can be misleading. Imagine we're identifying fraudsters, who constitute only 1% of the population. A model that always predicts not fraud would be 99% accurate yet completely useless. That's where business-driven metrics like precision and recall come into play. Recall answers the question: what percentage of actual fraudsters did we catch? Precision tells us, of those we flagged as fraud, how many were truly fraudulent. The balance between these metrics is a purely managerial decision. What is worse for us, missing a fraudster or mislabeling a legitimate customer? Now let's survey the landscape of algorithms that tackle these tasks. We can view them as a progression from simple to complex. We begin with linear and logistic regressions, fundamental, extremely fast, and, most importantly, highly interpretable models. They teach us core intuition, how to separate feature space with a simple line or hyperplane. Next, we move to more sophisticated methods like decision trees and their ensembles, such as random forests, which strike a strong balance between accuracy and transparency. At the top of this hierarchy lie powerful tools like gradient boosting, now the industry standard for tabular data, and, of course, neural networks, indispensable when analyzing highly complex inputs like images or audio. As we ascend this ladder, we gain power and precision but typically sacrifice simplicity and interpretability. Today, I'd like to focus specifically on two elegant methods, the support vector machine, SVM, and its regression counterpart, support vector regression, SVR. Imagine you need to draw a boundary between two groups of points. An SVM doesn't merely find any line, it seeks the widest road, that is, the hyperplane with the maximum margin from the closest points of each class. This makes the model highly robust. In contrast, SVR aims to fit a trend line such that as many points as possible fall within a designated error corridor. Why is this important from a governance viewpoint? SVM, for example, is a favorite of auditors and regulators. It provides a clear, mathematically grounded boundary and pinpoints the exact data points, the support vectors, that hold up that boundary. Those vectors can be examined for bias, making the model more transparent. Let us now view the entire model training process as a conveyor belt, starting with data, then data preparation, model training, hyperparameter tuning, and finally quality evaluation. Here, I want to draw your attention again. Annotation is crucial not only for training but also for reliable testing. The test dataset is your guarantee of real-world reliability. It's a distinct sample the model has never seen during training or hyperparameter tuning. Its role is to give an honest assessment of how the algorithm will perform under entirely new, unseen conditions. Whatever the model learned about patterns came solely from the training and validation sets. The test set remains locked away until final evaluation. No iteration or tuning should ever touch it. This ensures an objective measurement of performance. If the test set is carelessly or simplistically labeled, your accuracy, precision, and recall will be artificially inflated. You might see figures above 95%, but at first production deployment, the model will crumble on real data. Therefore, strict, meticulous labeling of the test set is no less important than for the training set. The test set lets you not only calculate average error but also simulate concrete scenarios. How often will the model miss a fraudster? How precise will its price predictions be? How many false alarms will it generate? This insight is vital for making informed decisions about whether the system is ready for integration into business processes. A model can perfectly memorize its training data, but only the test set reveals its weaknesses. If significant deviations appear at this stage, you must return to annotation or calibration, never rush the system into operation. The test phase check is the last line of defense against costly errors and reputational damage. A rigorously labeled test set is not a formality, it is a key quality control and risk management instrument for any AI project. Only honest, carefully labeled testing guarantees the model will survive its first encounter with reality. High-quality annotation is expensive. Labeling a single text comment can cost several cents, a minute of video annotation can run around $1. In AI governance, budgets must cover not only powerful servers but also the people and processes that ensure data quality. Underfund this stage, and you risk systematic bias that will later require mass remediation, at the cost of significant reputational harm or regulatory penalties. This brings us to a critical conversation about risks and controls. An AI model is not magic, it is a sophisticated instrument that can fail or misfire. Our task is to understand the main types of failures and the protective mechanisms we must embed. Let's examine the four principal risks. Data bias. Picture the model as an earnest but naive student. If we give it a history textbook in which certain groups are systematically portrayed negatively or incompletely, the student will learn those distortions as gospel. In AI, Training on historical lending data tinted by gender or racial prejudice doesn't just replicate bias, it amplifies and automates discrimination. This isn't merely a technical glitch, it is a reputational and legal time bomb. A model that systematically denies services to particular demographic groups is a fast track to multimillion-dollar fines, lawsuits, and lost customer trust. Our controls here are, first, a data audit before training. Do our historical data reflect the world we aspire to, or the one of past prejudices? Second, post-training fairness checks. Conceptually, these are like special exams for the model. We test whether its decisions treat men and women, or different ethnicities, equally under identical circumstances. We'll cover these audits in depth later in the course. Overfitting. This is the classic tale of a student who hasn't grasped a concept but has memorized every exam question. On the real test, they ace the questions they've seen but fail spectacularly with any variation. An overfitted model behaves identically. It memorizes noise in the training data, yielding phenomenal accuracy there, but misses the underlying pattern and crashes on new data. This generates a false sense of security. You glance at a 99% accuracy report, invest in product launch, and discover in production the model is useless. That is a direct path to misguided business decisions. The cardinal rule is never test on your training data. That's the essence of correct validation. Before training begins, you carve out a test set, say 20% of your labeled data, and keep it in a safe vault. The model trains on the remaining 80%, never seeing the test set. The final proficiency exam occurs only on the vault data. Additionally, regularization techniques act as penalties for excessive complexity, nudging the model to remain simpler and avoid fitting random noise. Model drift. A model is a snapshot of the world at a moment in time. But the world never stands still. A model trained on pre-pandemic consumer behavior became obsolete when buying patterns changed drastically. Data distributions shift, and yesterday's accurate model begins to falter. This silent killer of performance can erode business value over months. If unmonitored, in half a year your company may base decisions on entirely outdated logic. Controls here are straightforward. First, continuous monitoring, dashboards tracking key model metrics in real time. Second, trigger-based retraining. When metrics steadily decline, the team receives an alert to refresh the worldview by retraining on new, up-to-date data. The black box problem. The most powerful models, especially deep neural networks, often operate as opaque black boxes. They deliver remarkably precise predictions, but we cannot simply explain their rationale. Imagine a customer denied credit asks, why, and your reply is, because the algorithm said so. That is a direct path to regulatory noncompliance. For example, European law grants citizens the right to an explanation. Moreover, it undermines trust. How can we trust a decision whose logic we cannot understand? How can we improve or correct it? Our controls here involve strategic trade-offs. The first approach is to use interpretable models from the outset, sometimes sacrificing a fraction of a percentage point in accuracy in exchange for a transparent model, say, a decision tree whose logic you can sketch on a whiteboard and explain to any stakeholder. The second approach is to apply post hoc interpretability techniques. Later in the course we will devote an entire module to these methods. Think of them as translators that peek inside the black box and articulate its complex reasoning in plain language. In conclusion, when deciding to deploy a supervised learning project, remember, your focus must not be solely on algorithms, but on the quality of annotation, the rigor of evaluation, and the management of risks. These are what distinguish a successful AI project from an expensive academic experiment. Friends, ahead of you is our bonus quiz covering this lesson's material. Here are 6 questions to test your knowledge. What is supervised learning? What unifies the concept of labeled data? What is the fundamental difference between classification and regression in supervised learning? What is prediction error? Which metric answers the question, what percentage of actual fraudsters did we catch? What is the term for the risk where a model's performance degrades over time due to changing data distribution? Please pause the video and answer each of these 6 questions on your own in the comments below. We'll review interesting cases together. If you found this lesson helpful, give it a like and subscribe so you don't miss the next one. Correct answers and detailed explanations will appear in our Telegram channel, link in the description. So today we learned how supervised learning transforms labeled, feature plus label, pairs into reliable predictions. We covered the 2 core tasks, classification and regression, examined quality metrics and recognized the importance of risk controls. You met the primary algorithms, from simple linear models to powerful neural networks, and understood how to build the end-to-end pipeline from data collection through testing. I wish you success in applying these tools in practice. All the best, and see you in the next lesson.